This episode is brought to you by Honda. When you test drive the all-new Prologue EV, there's a lot that can impress you about it. There's the class-leading passenger space, the clean, thoughtful design, and the intuitive technology. But out of everything, what you'll really love most is that it's a Honda. Visit honda.com/EV to see offers.
Ryan, details.
Hello, Beat Check listeners. I'm Gosha Wozniacka, and I'm the environmental justice reporter at The Oregonian. Today, I'm with Burke Hales, a professor at Oregon State University. Professor Hales is the chief scientist at a new and unique wave energy test site just off the coast of Newport. This site is going to allow developers to test devices that can harness wave energy, so the power of waves, and turn it into electricity. And this electricity, one day, hopefully, can feed into the grid to power our cars, homes, boats, you name it. So today on our show, we're going to talk about wave energy, what it is, and its potential to help achieve a clean energy future, something that the US is racing to do, as well as the world. And we'll also talk about the purpose of the test site and what some of the challenges facing this new technology are. So let's get started. Welcome to the show, Burke. Thanks so much for taking the time to speak with me.
Well, thanks for hosting me.
Yeah. So let's start with the basics. I think many of our listeners may be familiar with offshore wind, since it's a controversial technology that has captured headlines recently. But wave energy is kind of a new topic. Can you tell us what wave energy is and how we'd go about capturing it and turning it into electricity?
Yeah, so wave energy is something that we've been aware of as humans for our entire existence. We've built structures to take energy out of waves on our shorelines, breakwalls, jetties, harbors, and we're typically deal with wave energy as something to be diminished and dissipated. And so what we're trying to do now is understand ways that we can capture that energy and repurpose it, redirect it into another form that we can use more beneficially. And so waves have a huge amount of power. Anyone who's gone to the beach, anyone who's surfed, anyone who's suffered through high sea states on the ocean, you know that the waves have a huge amount of energy. You watch the way the beaches are reshaped, and it's clear that that's the case. The question is, how do we take that kinetic energy of the waves, the movement of waves, and turn it into something more accessible, more controllable, more directable? And basically what we're talking about is capturing what we call oscillatory energy. Waves go back and forth, they go up and down. And so it's unlike water flowing through a turbine in a dam, which goes in one direction, or wind flowing through a wind turbine, which is a linear form of motion. And we're very good at converting linear motion into forms that can convert to electricity. Oscillatory motion is another challenge. Ultimately, the power generation technology is centuries old. It's been known since the early electromagnetic field effects were studied and understood. And if you can move coils of wire in the presence of a magnet, or a magnet in the presence of a coil of wire, electrical fields are generated, and those will drive electrical currents that you can capture. And so the wave energy devices themselves are, at the moment, a smorgasbord, a vast array of different technologies that allow the oscillatory motion of the waves to be to induce the movement of the generation of electromagnetic fields. And there hasn't largely been a convergence in a single best way of doing this within the wave energy conversion field. And what's needed really is a full-scale test facility where the devices can go in the actual ocean, experience actual waves, and prepare power that can be transmitted long distances, many miles from the source of generation.
Got it. So as you mentioned, there are devices to do this that would be floating in the ocean, capturing the wave energy and then sending it back to land, potentially. This sounds pretty complicated. What you're talking about, the Pacific Ocean is a pretty foreboding place to work in. We all know that fall and winter, the waves, the swells are really big in Oregon. There are many storms on the Pacific. So what are the advantages of this technology? Why are we pushing so hard if it is complicated to get this wave energy to land?
Yeah, so wave energy has got some differences from other forms of renewable energy that folks are more familiar with, solar
Hmm.
and wind, for example. We all know that the sun sets every day, and your solar generation capability ceases when it gets dark outside. We also know that winds can be highly variable and in some cases hard to predict. And so what's different about wave energy is that it doesn't stop. Waves don't stop when the sun sets. The waves persist. And we all know we've been to the beach on days where it's been light winds, but we still have large waves coming in from the open ocean. And so our shorelines are aggregators of ocean energy. Storms that might happen in the Gulf of Alaska, far from our coastlines, generate waves. These waves transmit across the ocean basins in ways that are highly predictable and well known. And so the wave power is this slower, steadier form of renewable energy in comparison to wind and solar. And so when you're trying to figure out how to put together a portfolio of renewable energies, having these persistent sort of baseline sources of energy are really beneficial. They're complementary to these more higher yield but more erratic and less predictable forms like wind and solar.
Hmm. And so would potentially help us achieve the clean energy challenge that's before us, the 100% clean energy that we're going for as a state, as a
Exactly.
country, as the
Exactly. And
world.
one of the things that's, yeah, right. And one of the things that's really important to understand is that there is no single green energy source that solves all of the problems. What we have to think about is,
Hmm.
again, I've used this term portfolio. We have to think about this distribution of renewable resources because we we need to be able to have predictable and distributable power, and you can't necessarily do that from a single source.
Yeah. So as you mentioned, wave energy is has advantages because it's a constant, predictable. There's lots of it around the world. What are the challenges uh, of producing and capturing wave energy
Well,
at scale?
yeah, you alluded to some of the challenges. I mean, just the environment that the developers have to work in, that the devices have to survive, is critically important. The ocean is it's violent. The very energy that the devices are trying to capture is also working to destroy those devices.
Mm.
And again, to call back to the example of folks, potentially being in a boat, you felt a big wave hit, you felt the boat shudder. You have to imagine that these devices are intended to be in that environment continuously for years. So
Mhm.
it's not as though there's bad weather coming and we'll all head into the port and wait it out. Those devices need to be able to survive those kinds of conditions. In addition
Yeah.
to that, ocean water is corrosive. Salt water degrades many of the things we build marine structures out of. It rusts, it corrodes. There's electrolytic activity if you don't have your materials very carefully thought out and protected. And in addition to that, anything you put in the ocean is ultimately is a site for marine life to habitat and to inhabit. And I'm talking anything from algae that will attach to the devices all the way up to sea lions that want to climb on top. And so
Mm.
you're talking about devices that if you put them out and they're pristine, just out of the shipyard state, they might perform in a certain way, but by the time they're out there for a year and they've got a 6-inch thick layer of gooseneck barnacles on them, they might behave completely differently after that period of
Mm.
time.
Interesting. Um, we mentioned at the start that there's a test site under construction in Oregon, and it's about to launch next year. Why Oregon? Why are we citing it here?
Well, Oregon has sort of a harmonic convergence of factors that are conducive for supporting wave energy testing devices. The first is that the wave resource, as we know, is highly energetic. The energy, the power that is in the waves that impact the Oregon coast is high. It's one of the best resources globally. Um, but the other piece of this is that the infrastructure, the civilian infrastructure, the power grid infrastructure is accessible to our coastlines. Oregon's got a long, proud history of publicly accessible coastlines. Our state park system is the envy of many other communities. And so we have communities that are on the coastline that are, on the grid. And if you look at, for example, the coastline of the state of Washington, or if you move up into Vancouver, British Columbia, or into Alaska, those coastlines are much more remote. There isn't the capability that's as readily available to put power that you might generate from waves onto the local utility grid. So Oregon really has this combination of great waves, great infrastructure, and as we'll discuss probably in more detail, we've had a really wonderful interaction with the coastal community in terms of siting these locations, making sure that we're working with the community, the fishers, the shippers, and that's been a huge benefit to this project.
Can you tell us a little bit about the history of wave energy? So, you mentioned that humans have been interested in wave energy for a long time. What about here in Oregon? Is this a completely new effort, or have folks tried to develop this technology but just haven't gotten it to a point?
So, if we go way back, Stephen Salter in Edinburgh, University of Edinburgh in Scotland, in the early 2000s, in response to one of the crude oil shortages, embargoes, built a device called the Salter's Duck, and it was an asymmetric platform that, in response to the waves, would wobble, and then that wobble would induce a rotational motion and would generate power. And so, there were, I believe, a couple of Salter's Duck devices that were placed in the ocean, 20 years ago. In Oregon, Oregon State University in particular, before my joining the project, was already at the forefront of wave energy generation. And there were a couple of devices that were tested just off of Newport in the early 2010s, 2012 and 2013, I believe. The first device was made by a company called Finistera, I believe. Finivera was a device that was deployed just off of Yaquina Head, and it produced power at the tens of kilowatt levels for a short period of time, but ultimately it fell victim to the ocean and it sank and had to be recovered. The next year, there was a device produced by a company called WetNZ, which is now being operated by Northwest Energy Innovations. The device was called the Azura device, and it tested off Yaquina Head in 2013. And it has since gone on and tested in a couple of other places, the Navy site off of Hawaii, and was active as an active Department of Energy award for a smaller scale device design, which was intended to test here in the next few years. But none of those were grid connected. All of those were what we call blue economy or non-grid connected devices that would generate power for a remote facility, an aquaculture facility, a fish pen, a vessel restocking kind of a station. And so what's new with PacWave South is that we're actually bringing the grid to the ocean, so the developers can deploy devices, generate power, electrically transmit it back to the grid.
Got it. And just to clarify, the blue economy is the economy of the ocean. So
Exactly.
Oil platforms or aquaculture farms, just whatever happens in the ocean that is tends to be pretty polluting.
Aids, navigational aids, ocean monitoring systems, the power for those being provided by waves as opposed to other forms of energy.
Mm-hmm. Yeah. So, you mentioned the previous devices, didn't generate a lot of power or were not connected to the grid or sank. Why will it be different this time? Has the technology advanced significantly? Is there just more of it?
Well, certainly the technology has advanced. It's been a decade more since those efforts. And there never has really been this kind of opportunity in continental U.S. waters for full scale utility scale devices to produce power that can be then transmitted to the grid. The sector has grown. The sector has gotten more support from the Department of Energy and others. And ultimately, we're now talking about having the capability to test these full-scale devices at megawatt power levels. That really wasn't available before, and so we understand to a much greater degree what it takes, what it costs, the kinds of things that need to be monitored, that need to be assessed, that need to be anticipated. And so, every device that is deployed in the ocean, it has to have a decommissioning plan, a recovery plan. So it's not, it's not like Walmart where you just build a building and then you walk away from it. You put something in the ocean and you're done. You have to recover that. You have to bring all that back in, and the financials of doing that have to be established ahead of time. You can't go out and say, well, we'll figure out how to recover it when the time comes. That needs to be something that you do with forethought.
Hmm. Interesting. I read somewhere that there's been about hundreds of devices of these energy converters that have been patented, but most of them have not been tested. So it seems like there's sort of a there's been a big development of technology, but it's all sort of waiting to actually be tested so that we can see if any of it works.
Yeah, and we see with outreach from potential clients and developers that might use PackWave sites. We see a lot of these very preliminary patents, but the patents sometimes are almost entirely hypothetical. They're a theoretical design concept. They're not really an actual device, and in almost every case, they are, you know, bathtub-sized devices. We call scaled devices. And so you go from the number of folks that have patented, conceptual designs or very small scale devices, 1,000 to 1, 100 to 1, downsized from the full scale device. There's a huge drop off between the folks who've gone to the level of testing at a facility like the Hinsdale Wave Research Laboratory at Oregon State University, where the devices might be 10 scale. And deployed in the tanks there. The reduction in technologies that goes from the conceptual level up to the 10 to 1 scale level is huge. The number of patents, the number of ideas, the number of concepts that never make it to that stage is large. And we're talking about another downscaling to go from testing it at the Hinsdale facility to the actual open ocean.
Right. Because there's only a few test sites around the world, such as the one that's about to come online in Oregon. I think there's one in the Orkney Islands in Scotland, and then the U.S. Navy test site in Hawaii. Those are the ones that I'm aware of.
Yeah, and that's just about it. There's some facilities off Portugal. There's a small facility in the Bay of Biscayne off of Spain. But the large facility that does this kind of scale testing is really the European Energy Center site at Orkney Islands in Scotland.
Got it. And how many years are we talking from where the technology is today to where it might be commercially viable and actually serve the grid?
Yeah, so my guess, right, and really this is not my expertise. I'm providing the support. Where PackWave is providing the support for folks to test this technology, and that requires a certain level of unbiased perspective. And so my projections are quite general, and so I imagine 10 years after the first full-scale test at PackWave, we may be talking about a commercial-scale device deployed somewhere. That somewhere is another question. Likely that the location that would receive the first of these devices would be somewhere that has a more challenging energy portfolio than the Oregon coast. We anticipate the devices at Packwave South will test for a couple of years at a time and then go on to their ultimate commercial deployment. And Packwave will continue to test devices without likely ever becoming a truly utility scale continuously operated facility.
Yeah. So let's talk a little more about this test site, Packwave. It was developed by the university with funding from Department of Energy. How long did it take to build, and what makes it unique?
Yeah, well, so how long did it take to build? We're almost done, so I guess I shouldn't guess what it's going to take. We anticipate being fully constructed and starting the commissioning and testing phase within the next couple of months. We anticipate receiving our first clients in the summer of 2025, and so if we're fully constructed in 2 months, we actually started groundbreaking activities in 2019. And so it's taken us in actual construction, 4.5, 5 years to get to this point. So that's only a third of the story because the preparation, the design phase was extensive. The permitting phase was nearly a decade's worth of work with a litany of agencies, both state and federal agencies, to get the site permitted. The siting itself, site selection, working with the communities to try to determine which location would be the best for this, that was another several years that preceded the permitting activity. So if you were to talk about when we really started trying to design this facility, it's been 10, 12 years.
Mm-hmm. Yeah, it's a while, and I wanted you to sort of describe this because I want folks to understand what it takes to build, this type of connection into the grid that will be needed for any of these devices to actually send electricity to the mainland.
Yeah, no, it's
Uh,
it's a large effort, and to try to imagine how the Packwave effort would scale up to an offshore floating wind facility. It's a large multiplier. It might cost 10 times as much
yeah,
and take at least as much time to get those
yeah.
sites permitted and constructed.
Yeah, very different technologies. What does the your test site look like exactly? Like, what can people expect to see from shore? Because that's a big
Yeah,
deal.
well, right now, well, if you were to go to the test site today, you were out with us last Friday, and we went to the test site, and it
Yep.
looked like any other piece of ocean. The
Yep.
infrastructure that we're installing, that we're constructing right now, is almost entirely either under the sea surface or underground. And
Hmm.
so the cables, the sea cables, in the ocean themselves are on the sea floor, and once they exit the site, they're actually buried below the sea floor. Before they come to land, they go into underground conduits, pipes through which the cables pass. The conduits themselves are sometimes as deep as 150 feet below the land surface, below the beach. They come into an underground vault that's below the parking lot at Driftwood Beach State Park. And really, all you can see from that spot is the manhole covers in the vault. And so it's designed to be an almost unseeable technology.
Hmm.
You have to be underground. You have to be underwater. You have to be on a vessel that's interacting with the cables, recovering them to the surface to connect to a wave energy converter device. So it's intentionally and necessarily a difficult facility to observe.
Got it.
We intend for there to be little visual impact, little
Yeah.
auditory impact of this facility.
What about the actual devices, the wave energy converters? What do they look like?
Well, that's a great question, and they look like 20 different things. If you were to go out and look at the technology that's out there at this scale, they look like giant watch winders. They look like large open-ended rectangular caverns with turbines on one end. They look like devices that just bob up and down on the surface. They look like devices that are segmented and ride on the surface of the waves. One of the things that's in common to all of them is that they all need to be near the sea surface. And so you don't generate much energy from a wave device if you're far up above the sea surface. And in some cases, the devices themselves are actually below the sea surface. That's a little bit safer environment to work in, and the devices can sometimes position themselves closer to or further from the surface if the waves are more optimal at a different depth. And so again, would a person from the shore be able to see these devices? In most cases, not. Everything that's out there carries required aids to navigation and automated identification systems so that folks know what's there and what it's doing to minimize conflict. The site itself is marked off with perimeter buoys so that everyone knows where things are. But as far as again, the visual scape, the site itself is about 7 miles out at sea, and if you could imagine a fishing vessel out that distance at sea, you'd see not much. The tops of the masts, kinds of things.
Interesting. So I was going to ask you, we mentioned at the beginning the offshore wind, that's pretty controversial on the Oregon coast. I suspect that wave energy isn't as controversial, maybe partly because of this visual aspect that it's kind of invisible.
Well, that's certainly a part of it, but there hasn't been necessarily, in the broader community, understanding that the visual impacts would be minimal. And so many of the public outreach events that we did, we were answering questions about, will there be a change in the lightscape because of these devices? Will they change the viewscape? And so those are easy questions to answer. The devices are far offshore. We don't, they intend to be, closely coupled to the sea surface, so not very vertically disruptive. But what really was the difference was that the Oregon State University community worked so hard with the coastal communities to identify the best places for these devices to go. They worked hard with the shipping communities, with the fishing communities, and ultimately the siting of the test facility itself was set by the fishing community. The folks in charge of the project in the early 2010s, Annette Bonjoan, Belinda Batten, were excellent ambassadors to the community, and so they took this project to the community, and the fishers chose a location that is outside of the shipping lines, not in highly fished areas for example, Dungeness crab. And so that was, ultimately the community dictated the siting, and that made a huge difference in how we're received by the community, how the community interacts with us. And so it was very definitely an engaged and cooperative process with the coastal stakeholders.
That makes a big difference because, with the offshore wind, I know one of the criticisms is that the community hasn't really been at the table, or their views have not been heard by the federal government. So it sounds like that makes a big difference when the community feels heard and included.
Yeah, huge difference.
One other aspect that I wanted to ask you about is impacts on the environment and marine life. So obviously these are, cables, devices that we're putting into the ocean that will interact with fish and other marine organisms. And so I'm wondering, this is new technology. Obviously, we don't have energy converters floating out there right now. But have researchers done any sort of proxy studies? What's the thought around how this will impact marine life?
Yeah, it's we like to say that nothing has ever been harmed by a wave spill, and so we don't have a product that is a potential contaminating product. The devices themselves, they move slowly, right? Waves do not move at the speed of a wind turbine, and so and they're large, they're obvious in many ways, and so the possibility that there are like a vessel strike on a marine mammal, very, very low. These devices are stationary; they move with the waves, and so we don't anticipate those sorts of things being problems. The big issues that are we believe will not be significant, but that we are carefully monitoring are acoustic disruptions. And so, of course, we know that we have multiple populations of marine mammals, gray whales that have different migratory patterns, some that are very close to shore, some that are further offshore. There are a lot of humpbacks, there are a lot of fin whales in the area. There are actually southern populations of orcas that come here and hunt salmon and other whales. I don't know if I should say fortunate, but I've been on the water off the Oregon coast and witnessed an orca attack on a cow and calf humpback. And so there are huge diversity of marine mammals that use echolocation and are very sensitive to disruptions in the acoustic environment in which they live. So we have, as part of our permitting, a commitment to ongoing acoustic monitoring of the site, and based on what we call exceedance thresholds, noise that is above the background. There are response measures that we have to take to identify the source of the noise, plan a mitigation for it. Now that said, these devices, there are no internal combustion engines, running wave energy devices, right? So the high frequency combustive noise sources that you might expect from an outboard motor or something like that shouldn't be a part of this portfolio. And anyone who understands the efficiency of devices, when devices start making noises, that usually means something's wrong with them. And so folks who've been around gasoline engines, when they're backfiring, when they're knocking or pinging, that's telling you something's wrong with those devices. And so these devices are intended to capture energy without wasteful energy byproducts, and noise is a wasteful energy byproduct. And so we don't anticipate these being significant acoustic disruptions at the frequencies that matter to marine mammals. But we're monitoring that continuously, basically for the life of the project. The other thing that is maybe a little bit more equivocal is that the location that the fishermen selected is, I wouldn't say it's featureless, but it's a fairly low relief sandy bottom area. Doesn't have a lot of rocky structure. We're going to put anchors and cables there. And there will be animals attracted to those features, those substrates that are there that weren't there before. We know from our oceanographic monitoring programs that any buoy that you put out in the water gets sea life interaction with it. The gooseneck barnacle example that I gave it's one of the most common forms of what we call biofouling. And a gooseneck barnacle might be 8 or 10 inches long, and they'll populate the entire surface of the device. There will be fish attraction. Rockfish, lingcod that like structures like these are likely to be attracted to these devices. And so those are things that we anticipate playing a role. And so I think the idea that you can ever just put something in the ocean and have there be no effect is naive. We know there will be effects. Yeah. How those effects interact with the system, will these behave like artificial reefs and increase substrate for animals to aggregate upon? Maybe. We don't anticipate that the presence of this structure will cause detrimental effects to other organisms.
What about electromagnetic fields, since we're talking about sending electricity in and out?
Yeah. So the electromagnetic fields associated with power transmission are quite well understood, and it's highly dependent on the medium through which the power is being transmitted. So the power that will be transmitted through these cables goes through three large gauge copper conductor cores, each of which has very, very thick insulation jackets around them, an additional layer of electric shielding around that insulation, layers of armor, steel armor around the cables, and additional layers of insulation and jacketing. Furthermore, the cables will be buried below the seafloor, and our target is a meter burial depth. It might be a couple of feet. We're working on that project right now, and on top of that, seawater is a conductive fluid, and those of you who remember your freshman physics classes in college, you don't have an electrical field inside of a conductive medium, and so the dissipation of electrical field from a cable like ours below the seafloor through this conductive fluid, it's those sorts of things have been modeled by very well established laws of physics. The spread of the electric field from the cable itself is expected to be very, very small. We do have requirements to monitor this EMF, but the expectation is that it will be demonstrated to be almost immeasurably small, and once that's the case, continued monitoring won't be required. It's very different than thinking about power lines overhead. Air is a terribly non-conductive medium, and so the fields that you hear, the crackling, the humming, that wouldn't be the case if those were insulated wires going through conductive fluid.
Interesting. Thank you. So what happens next? You mentioned construction is wrapping up. You'll be starting next year. What is going to be the university's role now that the test site is pretty much done?
Yeah, so we have to be, neutral facilitators of objective testing of these devices. And so the university will continue to operate the facility in partnership with the Department of Energy's National Renewable Energy Laboratory and the Pacific Northwest National Laboratory are going to be key partners with us in this process. Our anticipation is that we'll work with DOE funding with those partnerships for the next couple of years, and that the Department of Energy will continue to support developers in their production of devices to come and test at PacWave. The funding model and the business model beyond that couple of years is something that will continue to adjust, and it may be that at some point in the future we become a facility that can be supported by user fees as opposed to direct funding from the Department of Energy. The near term, the foreseeable future has us working closely with the Department of Energy and the national laboratories to keep this facility going, and basically to make sure that the concepts that are out there can get rigorous and unequivocal testing of the technology so that we can start to converge on a best approach, much like we see with wind turbines. Wind turbines now look more or less all the same all around the world. But that wasn't the case 20 years ago. There were many, many different wind turbine designs that had not been optimized for what we're seeing today.
Mm-hmm. And you'll be doing quite a lot of monitoring too, right?
Oh, absolutely. So we monitor not only the environmental impacts and the site conditions, so the wave fields, the current, the wind fields, but also the power produced by these developers. We're monitoring those at the point of grid integration, so that we are, the final auditors of what a developer is producing. And so, a developer may have incentive to characterize their device's output more optimistically. They may be able to produce a lot of power at the device itself, but not in an effectively transmittable form. And so that's really ultimately the final proof of this, is that we'll have the ability to, through our own independent monitoring capabilities, assess the quantity and the quality of the power that these developers produce.
That's great. Last question. I know that you're the facilitator of this test facility, not the builder of devices, but you've been working on this for some time. I'm wondering, what's your hope for the future when it comes to wave energy development?
Well, so I would love to see, the seaworthiness, the survivability of a device. We're capable of supporting devices that can produce 5 megawatts peak. I would love to see a device that was reliable in the ocean and could produce megawatt level power with ultimate deployment at a location that may have a greater need for this kind of renewable power. And so we talk about remote locations where there isn't the same sort of hydropower resource that we have. There isn't the same sort of broader network grid capability, and those are the kinds of locations where this type of renewable energy could be quite useful. Think about high latitude areas where the sun doesn't shine for several months at a time, and solar is not a particularly viable year-round energy provider. But wave might be a fabulous complementary contributor to a place like that.
Got it. Well, thank you. This has been a really important conversation, and we'll be following this topic in stories at the Oregonian and at OregonLive.com. And I'm going to drop a few links to relevant stories in the show notes. Thank you so much for listening to Beat Check with the Oregonian. If you like this show, please give us a 5-star rating and review in Apple Podcasts. It helps people find the show. The best way to support our journalism and stories like this one is with a subscription to Oregon Live. You can do that at OregonLive.com/podsport. Until next time.